Okay, welcome back to Love and the Physics of Mr. Goldthorpe. Here's a gentle lesson on pendulum motion. Turns out pendulums can move approximately in simple harmonic motion under certain conditions. And the formula for the period of a pendulum is very similar to the one for simple harmonic. It is T is equal to 2 pi root L over G. Now I'm not going to show you the derivation, it's very complex. So instead, we're just going to talk about what you need to know about it. First issue is that this one only works if the angle is less than 15 degrees. So if I put the angle kind of on this diagram, this angle right here, that angle theta has to be less than 15 degrees. So it has to be a very small angle for this one to behave like simple harmonic motion. If you make the angle too big, it starts to break down. It doesn't work anymore. That's our first condition that you need to be aware of. Good, I'll get rid of that. Now let's talk about L. You have to realize that L is specifically from the axis, or the fulcrum, all the way to the center of the mass. So distance from the length to the center of the mass. That's important for a lab, and that's important if we get you to measure with a ruler on our life-size diagram to the center of mass of the object. And really, that's all you need to know. And interesting enough, the relationships are very similar. This one actually says that the longer if you look at, we have T being proportional to square root L, if G stays constant, that means the longer the pendulum, the greater the period. And it turns out that's the only thing that affects it apart from gravity. Well, we need to see that. So let me take you to a video which illustrates that point. So I'll go back over to my drive here. Let's get out of here. Okay, and let's go back here. And I just got to find pendulums. There we go. Okay, so here's a pendulum video. And we have two masses that are exactly the same length right now and exactly the same mass right now. So same length and same mass. And what we're going to do is we're going to take one of these pendulums and displace it, let's say 5 degrees, and then release it. Now it's going to oscillate. I'm going to slow it down a bit. And I'm going to take the other one and move it to an angle of, let's say, 10 degrees. I've doubled the angle. So I've doubled the angle, doubled the amplitude. And I'm going to release these things at the same time. And how do you think their periods will compare? And release. Okay, well, you can see that the blue one's moving faster, but the period is identical. So it has no effect. Amplitude has no effect on period whatsoever. Okay, that's convincing. Let's change something else. So what we're going to do now is we're going to change the mass of one of them. We're going to make one of the masses really small, like 0.5 kilograms. The other one big, make it 1.5 kilograms. So I'll take one of the masses, in this case, the larger mass, and move it again to 5 degrees. Oh, let's move it to 10 degrees, okay? And then release it. And I'm going to move the other one to 10 degrees as well. So they have the same amplitude. Not that that has any impact. And then I'm going to release them at the very same time. Released. Good. And you notice they move identically to each other. So it doesn't matter how big the mass happens to be, they move identically. So mass has no effect on the period of a pendulum. Rather surprising. Well, something's got to affect the period. Do you guys remember what thing does in fact affect the period of a pendulum? Well, I'm going to bring the masses to the same again, 1 kilogram. Let's now change length. I'm going to make the blue one have a length of 50 centimeters. Now I'm going to take the 2 and move it again to a displacement of 10 degrees and release it. Now, if I release the other one, how do you think they're going to compare? Feel the drama. Now we release it, bring it to normal speed. Okay, now they're no longer the same. And can you see that the shorter one, smaller length, has a very short period. Okay, smaller the length, smaller the period. Kind of like a direct relationship. All right. Let's now move back to our lesson. Okay, so now we've discovered that length has kind of like a direct relationship with period. Smaller the length, smaller the period. Direct root relationship. All we need to do now is do an example. And I'll do that in the next part of the lesson. I'll see you then.